Folks, in this video tutorial, I would like to show you how to perform a harmonic response uh, or what is known as steady state dynamic in the 3D Experience Release 2022x. Okay, the idea behind harmonic response is that you have an elastic object obviously under small deformation, so it's really a linear problem. And we are interested in predicting the behavior of the structure when a sinusoidal load is applied or sinusoidal displacement is applied at a particular node or a group of nodes. So in this particular in this video tutorial, I will be using shell elements, although probably it is best if you solve this problem as a beam geometry. So here's the problem that we're dealing with. We have a simply supported beam of a given dimensions that you see in a second, which its internal or the midpoint node here, midpoint location, mid location is on the sinusoidal load, okay, of a given frequency. Incidentally, this can be viewed, this little omega here can be viewed as the angular speed of, for example, a uh, uh, angular speed in radians per second of a motor which is unbalanced. Okay, so this little omega and that big omega are intended to be the same things. Okay, now uh, the geometry of the problem is that this is 1,000 millimeter long, so 1 meter long. Okay, the height is 100 millimeter long, so that is 10 centimeter, 100 millimeter, and the thickness of this geometry is 10 millimeter. So when you think about it, this is very suitable to solve as a beam plot problem. In other words, model this entire structure as a straight line and divide it into beam elements because of the nature of dimensional. However, I would like to solve it as a shell problem. In other words, I will model this thing as a plate and mesh it, and then the thickness of the plate is 10 millimeter that you'll see. Now, it is made of steel. These are standard properties of steel. And the angular speed, this angular speed of this motor, if you think about it, or that omega is 900 radians per second, which is 143 hertz. Now, I'm going to assume that it's an undamped motion, and uh, the geometry is going to be meshed. You'll see in the next slide. However, I want to point out that if this problem is viewed as a beam problem, okay, there is an analytical solution. The analytical solution, which is vertical displacement of the midpoint of that simply supported beam, is given by that expression. Notice that this is all a constant. This thing is all a constant, okay? And there are infinite number of frequencies. They're all calculated like that. These are the modal frequencies of the simply supported structure, okay? In plane, in other words, does not move out of plane. And this is just multiplied, this entire constant is just multiplied by a sine function. That's the whole idea behind steady state dynamics or linear dynamic problem. Okay. Now, steady state dynamic problem. Now, just be careful that although I will use the results of this analysis uh, and compare it with this, but I don't expect to get necessarily a good accuracy, okay? But they should be roughly in the same ballpark, okay? Now, the problem that I'm going to do is that that sheet that I talked about, or that beam, is modeled like that with shell elements. These are parabolic shell elements. And I will only use 10 modes, prevent this thing from moving out of plane, okay? So it remains in the plane that you see. It does not move perpendicular to it. And I will use only 10 modes for this purpose because when you do harmonic response or steady state dynamics, you have to decide how many modes you're going to be using, okay? And those modes, those modes or frequencies uh, first have to be extracted in 3D experience, and then it will be used to do the steady state dynamics, okay? So that's what we're going to do. All right, so let's start with because we're dealing with shell elements, we need surfaces. Let's start with a generative shape design. Okay, there we are. And let me rename this thing to, let me call this thing harmonic response. Harmonic response, so that I can find it easily in case I have to search. Okay. All right, so on that vertical plane, on this plane, which is YZ plane, I will sketch a rectangle of those dimensions that I mentioned. So let's sketch a rectangle. Mention it. This height was 100 millimeter. 100 millimeter, yeah, okay. And that is 1,000 or 1 meter, 1,000 millimeter. And let's fit this thing here. There we are. Okay. I would like to put a surface through that, so I can go to uh, exit. First of all, exit the sketcher. Okay. And then we go to surfaces. There's the fill. We're going to fill that particular sketch with the surface. And there we are. Incidentally, to avoid picking that sketch, I'm going to hide it. So I expanded this thing right click and I hit the sketch. Okay. Now let's create our material properties. So we're going to go to tools, create material. Let me call this thing I don't know, harmonic. This is just a name. Harmonic response video. Video. All right. So okay. No, I haven't input the material properties yet, but I will do in a few minutes and in a minute. So it's right there. Right click, apply. Okay, I'm going to close this window and apply it to that. Check mark, apply, select a check mark, and there we are. Okay, so this is the name that I gave it, right? And double click on the, uh, the branch here. It opens up the dialog box, so it's a structural problem. General option, the density is 780, I think it was 7800 kilogram per meter cube. And then we're going to go to abacus multiphysics, mechanical, elasticity, elastic, and this is 200 GPA, 200 GPA, and Poisson ratio of 0.3, 0.3. Incidentally, notice that I didn't change the units in my preferences, so that's why I converted 200 GPA to imperial units, which is roughly 30 million PSI. But that's okay, that's all we need. So we say okay. Now, we're good. So let's save this thing. We're going to be do the meshing right now. Okay, so we're going to go to uh, structure model creation, MTFEM. Okay, so under meshing, we're going to use the surface quad mesh right there. And I put 15 millimeter here, 15 millimeters, which is incidentally 0.5 meter. There we are. And we're going to use the quadratic or parabolic, same thing, and mesh it. And there we are. And okay, so what you see there is actually this mesh. Okay. All right. Now, while we are at it, let's do the properties shell section. For that, we can select it from part body or from the screen, and we put down 10 millimeters, right? The thickness of this was 10 millimeters. All right. Incidentally, you notice that there are exclamation marks here, or there are update request markings here. So if I update it, these are going to disappear right there. Now, I don't want to see my geometry, so right click, so under visualization management, I don't want to see my shape, my part, so unhide or hide, there we are. Okay, all right. While we are at it, let's create a group because we want to apply the load at this center node. Although you might say, wait a minute, this thing that you showed me looks more like wanting to apply it on the top. I know that, but I will apply it in the middle of that sheet. Okay, so the first thing that we need to do is to create a a, a group making consisting of that one node, because at that one node, what you would like to do is to apply a load and then plot the load versus deflection, or deflection versus frequency at this node. So let's go ahead and create a group here, manual group. So this is, I think this is exactly the middle one. See now, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep, that's exactly the middle one. And let's call this thing node of interest. Node of interest. Node of interest, because that's where we apply the load and we want to find deflection later on. You say, okay, we have created a group, a manual group. You see that right there, right there. Now, we are done as far as this issue is concerned. So we're now going to go and create our scenario. So we go to structural scenario creation. Okay, so let's, for the final model, we have only one that we already selected. It's right there. You can see that. Okay, good. Incidentally, while we are at it, let me rename this physics, this default name into uh, harmonics response. Harmonic response. Response. Okay. Response. Okay. Good. Once again, I don't want to see that shape, so right click mesh visualization. I don't want to see my part, so hide it. There we are. Okay, so first of all, the uh, plate, this thing cannot move out of its plane, so this surface remains in the YZ plane. So before I do that, let's go ahead and specify our procedure, okay? Procedure, you have to extract, I want to extract 10 modes of this. So the 10 mode, we go to frequency step. First we do a frequency step, and the default extraction number of extraction of frequencies is 10. So I'll just leave it the way it is. You can use more, you can use less, whatever you want. So first step is actually a frequency step. You can see that. Now, we go to restraints. First, we take all points in this plane and say, do not move in the direction X. So you select the find fixed displacement, select, you can select that surface. There, okay. I selected the fill, okay. Right, and do not move in the direction X. Okay. Now that doesn't show, oh, right there. See that? Does not move in the direction X. Okay, good. Now, this point cannot is a simple support, so does not move in direction Z or direction Y. So another one where we do another fixed displacement, that's this point. There, fixed displacement. You may have a hard time picking this point, but you have to do your best. So now this does not move in the direction X, but now I don't want it to direction Y or Z. Very good. And finally, this point can only move, because it's on a roller, can only move in the direction Y. It cannot move in direction Z. So a third one here, that point, okay, does not move in the direction Z. All right. Okay, so because we're doing a frequency step, we don't need a load here. So actually everything is done. So we go to simulation. Let's first of all check it, model check. We're going to get all our 10 mode shapes and frequencies. Okay, it's working on it. Done. Let's do the simulation check. This is to make sure that things, if there's things that are dramatically wrong, they may show up in these check steps. Okay, and it seems that at least the first one was fine. So let's do the scenario check. Well, this is going to be okay too. And once it finishes, then we're going to run it. Okay, it's done. We're going to run it. Okay. Okay, it's working on it. All right, so the 10 frequencies are going to be popping up in the units of hertz, and the corresponding mode shapes are going to also appear. Okay, so you can see that. So let me close that, make this thing smaller so that you can see what's going on. I don't need this. Okay, so if you look at this thing from the front view, front is right there. So this is the first mode shape, and there's the frequency, second mode shape, etc. Okay. Right. Incidentally, if you look at the smallest frequency here from there, if you set n equal to 1, you will get something that is close to this first number. Okay. I think you're going to get around 219 or 220, something of that. And these are the other mode shapes. Okay. Now, this is terrible because the mesh is, my mesh is not good, but anyway, I just want to show you how the process works. I'm not making any claims on the accuracy. Okay, now, the next step is the following. First of all, yeah. So these are the results that are generated. Let me deactivate the displacement. There, okay. Okay, now, by the way, if I want to see the mesh here and I need it because later on I want to put a load on it, you can do that, but let's not worry about it right now. So we go to the scenario again. So under standard, we go to scenario. Now we're going to create our second step. So procedure. This is going to be second step, which is harmonic response right there. See, you go down this list. First, we did the frequency step, we need it, and now we're going to do harmonic response. Okay, so the question is, you want to do harmonic response. In other words, look at the effect of this this problem for frequencies between 0, 0, and let's say lower value 0, upper value 1000 hertz. Okay. Suppose we want to do this, and the increment we just leave it the way it is. So increments of how about maybe 10 hertz. Okay. And then use all the modes, eigen mode, use all the modes, use all the modes, all modes, okay? And then we say, fine. Okay. Now, we're gonna apply a load, a restraint, a load right there, right at the middle node. So we go to load. Now notice that I don't know where that thing is, although it's not necessary because I already created it as a group. Remember a group which was nodes of interest, okay, or node of interest. So we're going to say this. We're going to say, okay, here's a force there, okay, and we're going to support is by group, and that's going to be node of interest. I just want to comment to you. I just want to tell you that unless you put it in a group, you won't be able to pick the nodes from the screen, okay? So we put it in a group and then load of minus 4000. It really doesn't matter whether it's plus or minus, but I'll make it 4000. And uh, this is pretty much it. So we say okay. Oh, it's the wrong direction. It should be in direction Z. So let's go ahead and fix this. Under load, load is here. Double click. This is 0, and this is minus 4000. Okay, good. And now, because I want to plot the displacement of this point, uh, we know that the displacement of this point is sinusoidal. We know that, but we want to know the amplitude of it as a function of frequency. So all we have to do is we have to actually go ahead and ask for that. And asking for that is under, you'll see under simulation, right here. This is where you ask for data, output. So first of all, not the whole model. I want the group, and the group is that node of interest because I want to plot the history of that, not the field, history of history here doesn't mean in terms of time, it means in terms of frequency. Displacement, translation, okay? And if you also want to look at the distribution of the stress and displacements and things like that at every point in color, then obviously you have to also ask for the field output. So this is one that I just did, okay? And then you can also ask for the whole model field. For example, you can ask for, I don't know, is stress. How about that? Stress. Okay. Otherwise, you can see that first graph, which is the amplitude of the displacement as a function of frequency. That's it. Okay. But if you want to see the stress distribution, you know, and things like that at every point in the model for a particular swept frequency, then you have to ask for the field model also. Good. That's pretty much it. So let's go ahead and first of all check it. I don't think there will be a problem. And then do a simulation check. Make sure nothing critical you left out. And finally, we're going to run it. This is just a check. If you want to see this problem done as with beam elements, I suggest you go to the playlist that I have, which is 3D Experience, Finite Element 3D Experience, or 2021x. 2021x. There is a playlist which is a bunch of problems, and this is one of them, and it's done with beam elements. Look at the one which deals with chapter 15, please. And we're going to run it. There it's done with beam elements. We can easily do this thing with solid elements also. Okay, it's running. Don't worry about this message that you get here. Okay, so I also want to remind you, when you took your differential equations course, the instructor said if you have a second, or if you have a linear problem, for example, second order equation of motion, linear, and the right hand side forcing function is a sinusoidal, then the displacement or the solution is also sinusoidal of the same frequency. Okay, first of all, right there, let me close this right there. So remember, we took a lot of yeah, this was the first one. There's the second mode, etc. Now, if you want to know the displacement, okay, second. Oh, this is the frequency step. I'm sorry, that's not what I want. Harmonic step is what I want, right there. Harmonic step, I was looking at the frequency step, the modes, okay, that's not what I want. I want to go to the harmonic step, and there's a lot of them. There's 100, I believe. I swept from 0 to 1,000 hertz, increments of 10 hertz, so there's 100 points here, and each one of them I can get, for example, the one Mises stress, okay, etc. But that's really not, this is coming from your, what is called the field output, but that's not what I want. Okay, so let me go ahead and do a plot, history plot. You can see that history plot, or XY plot from history. And then let's go to scroll down here, translation and magnitude, or this translation direction. You know, Z will do, because really this does not move in direction X anyway. Magnitude or displacement direction 3, really doesn't matter. Okay, so let me make it, well, yeah, okay, direction 3, fine. Now we want, that's pretty much it, apply. Okay, there we are. So what this graph gives you is the frequency response. In other words, as a function of the frequency of the applied load, what is the magnitude? What is the magnitude of the displacement of that center node? Now, first of all, because I have no damping, this goes all the way to infinity, and this is your first natural frequency. So there's a resonance here. But if my frequency of interest is 143 hertz, then what I can do is, what is that the magnitude of displacement? So I'm going to click on this icon here. It gives you that line, and you can move that line to the frequency that you want. At the very bottom, you can see it gives you the X value, which is the frequency of the applied load. So if I go to roughly 143, right there, or this 147, roughly something there. Okay, good. It gives you the value for displacement, magnitude of the displacement, amplitude of displacement. It gives you this number, 0.0009 meter. So that is uh, 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 this is this thing is going to be in the same ballpark as this value. See that? This value, this entire value, we are saying that it is approximately 0.3009 meter. okay? So roughly 0.9 millimeter, right? 0.9 millimeter, okay? Or yeah, 0.9 millimeter. Now, uh, do not try to get exact. If you do this number exactly, you're not going to get what we have here. But because this is done for beam model, and what we are doing is shell model. So you can see, for example, if you go here, and if you see, if you move this thing to roughly 219, 220, the magnitude becomes very large. In fact, in theory, it goes all the way to infinity. Now, you can look at the effect of damping by adding modal damping, which I'm not doing in this particular video tutorial, but it can be done if you desire. So we'll do some other videos on damping later on. Okay. Okay. Good luck, folks.